Hello everybody. Please give me 1 minute to make sure that my stream is actually working. There we go. It appears to be working. This is good news. So welcome back to my basement. I discovered too late yesterday that neither of the class videos that I thought I had recorded actually made it to YouTube because they changed their streaming interface and my software was no longer connected properly. So I am trying to make up videos to show you what you missed in case there are students who are unable to attend or they just want to hear it again. So this is my best recollection of what we covered yesterday, October 1st in SEM. So here we go. We were looking at example 4. Just to recall, this example has 6 items that are measured on a 1 to 7 scale that we're pretending is sufficiently normal. And those items are thought to indicate a single latent trait of forgiveness of situations. So your ability to get past things that happen to you that are no one's fault. And this was the standardized solution that resulted from a one-factor model. So I want to point out with respect to the standardized factor loadings here, those are in a correlation metric. They provide the correlation of each of these indicators with the factor. So the factor is the single predictor for these 6 outcomes. And based on this information, it looks like items 1 and 3 are relatively stronger than the rest, so the factor has more to do with them, so to speak. If we take these standardized loadings in a correlation metric of R and we square them to make them R squares, then we get these values down here, which give us the proportion of variability in each item that is thought to be attributable to the latent factor. So for instance, item 1 is thought to be 50% factor, 50% not the factor. Item 3 is supposed to be 60% factor and 40% not the factor. And because CFA is a linear model of the latent trait in predicting the response, a linear model means that we have a constant slope that's equally good at all levels of the trait. We are assuming that if an item is good, that it's good for everybody, meaning that we don't need to pay attention to item difficulty or the location of the item on the trait according to this model. In practice, because these items are bounded, the line does have to shut off at some point. This is going to be an overly optimistic view, but in the context of CFA, if an item has a strong loading resulting in a large R square, that item is thought to be a good item for everyone. Pausing to make sure that the stream is still capturing. I'm superstitious today. Okay, it does look to be good. All right. So then the thing that we were talking about on Tuesday is how do we know if this model is any good? There's nothing here that tells us the extent to which the pattern of correlation across the items that these standardized loadings predict, or alternatively, the pattern of covariance across the items that the unstandardized loadings predict, whether that pattern actually matches what's in the data. And so we were looking at ways of identifying global fit and local fit as a way of saying whether or not our model is in fact consistent with the pattern of correlation in the data. So assessing global fit, we scroll forward until we get to that information, is a function of how tall our model is relative to how tall the best possible model is. So in terms of what our model consists of, we first want to consider degrees of freedom. So the total degrees of freedom is a function of the number of indicators, V. There's a formula here for that, but you can think of it more generally as the number of total means, variances, and covariances among the items that are part of your factor model. So there's 27 possible parameters that we can estimate because there are 6 means, 6 variances, and 15 covariances. Our model has spent 18 of them. And we know that as part of the M plus output here, it lists the number of free parameters. What free means is free to not be 0, free to be something that is found as part of the likelihood estimation process. So we have spent 18 because we have 6 indicators. Each indicator has 3 parameters. Each indicator has an intercept, a factor loading, and an error variance. So 6 times 3 is 18. We do not have any structural model parameters, which would be factor means and covariances. Factor means, factor variances, and covariances. We don't have any factor covariances because we only have one factor. We don't have any factor means because it had to be fixed to 0 for identification, given that we have estimated all of the indicator intercepts. And we don't have any factor variances because it had to be fixed to 1 for identification, given that we've estimated all of the factor loadings. So 27 possible means, variances, and covariances in the indicators, minus 18 parameters spent, free to be not 0, leaves us with 9. So more generally, because each item gets its own intercept, that is going to take care of the item means. Each item getting its own error variance is going to take care of the item variances. What we're really talking about here is the ability of the factor loadings to appropriately predict the pattern of covariance across the items. So there are 15 covariances to be had in the data. We have 6 loadings that are trying to predict them. So there's 9 degrees of freedom remaining. So the first thing that we're getting in the output with respect to global fit is the height of our model. And as you may remember from last time, you are the HO. You are the HO. That refers to the height of the data under your model. And these numbers don't mean anything in absolute value. The reason that it's a negative number is because this is height in a log metric. They only have meaning relative to comparison models, and the comparison model that is most relevant here is the H1 model, which is the best model. This is what's known as the saturated model. It is what results if you simply let your data be whatever they want to be. So rather than trying to predict the means, variances, and covariances of your indicators, you just let them be whatever they want to be. So you spend all your degrees of freedom to perfectly recapture your means and variance covariance matrix across your indicators. And this is as tall as your data can be. So it's a 6 by 6 matrix in this case. This is the maximum height given the data. So we want to compare the height of our model, so the height of the data under our model, relative to the perfect model. And what we're looking for is that our model does as good a job. So it gets as close to the height as possible, but it does so using fewer than all possible parameters. So we're going to get in a moment a direct comparison of these two heights to see whether or not our height is significantly worse. Before that, though, we pass by these things here, which are information criteria. These are the same things that are found in other areas of statistics. They're transformations of the log likelihood times minus 2 that are adjusted for the number of parameters in the model and/or sample size. So for instance, the AIC is the minus 2 log likelihood for the model times plus 2 times the number of estimated model parameters. The BIC is the log of the sample size times the number of estimated parameters as the adjustment factor. And these are in smaller is better form. So these tend to be used to compare non-nested models, models in which you cannot describe one as a subset of the other, and they are not significance tests. So smaller is just better, but there's no distribution associated with these where you can say how much smaller is significantly better. There's none of that. What we can say with respect to a significance test is right here, the chi-square test of model fit. What this is a comparison of the height of the data under our model relative to the height of the data under the best possible model, so as tall as the data can possibly be. Normally in statistics, we would take the difference in these two heights multiplied by minus 2, and that difference times minus 2 would be distributed as a chi-square. However, because we're using robust estimation that has these scale factors, we also have to take them into account in conducting this test. So just to recall, these scale factors are an index of how far off from multivariate non-normality our data are, multivariate kurtosis in particular, where 1 means that it would be perfectly normal, and the positive values mean that the tails are a little bit heavier than what they're supposed to be. So those two numbers, scaling factors, go into the formula along with the HO log likelihood and the H1 log likelihood. M plus does the math for you. And the difference between those two heights is a chi-square test statistic of 308. So for 9 degrees of freedom, meaning 9 more parameters left over that we could have estimated but didn't, that chi-square test generates a p-value with that 0 to 4 decimal places. So we have a significant result, but in contrast to what we would usually say, significance is not what we want here. What this means is that our model fits significantly worse than the saturated model. Our height of the data under our HO model is significantly shorter than the height of the data under the perfect model. So our model is not yet good enough. And M plus gives you a note to remind you that so long as you're using one of these types of estimation, MLR is what we have here, that this significance test has to incorporate the scaling factors. And more specifically, here is the formula by which that chi-square value was computed. So we have the difference in the model that has fewer parameters minus the model that has more parameters, so minus a minus makes a plus. And then we have the scaling correction factor that takes into account the number of parameters in each, as well as the scaling factor of each. And then we end up with a rescaled minus 2 log likelihood difference divided by the scaling correction factor that works out to be our chi-square of 308. And as I showed in class, I did build you a spreadsheet that does this. So this spreadsheet is posted along with the other files for example 4. I'm going to pull up the MLR Comparisons Table 2 tab to show you where this is. So the significance test that is done for you for the model, I recreated in here just to show you where the calculations would come from. So in this spreadsheet, you are to enter the values in cells A, B, C, and D, or excuse me, columns A, B, C, and D. You would describe the model, so this is for your reference to remember what you're testing. The model that has fewer parameters goes first, the model that has more goes second, and you give the log likelihood under those models. So this is the log likelihood for the HO, this is the log likelihood for the H1. The scaling factors that are given in the output, and the number of free parameters, which means the number of estimated parameters. Given these 6 pieces of input, the rest of the cells are calculated for you, resulting in a chi-square test statistic, the degrees of freedom, and the exact p-value. So that's where that number came from. Just as an aside, to give you a sense of what it would look like in M plus code if you wanted to fit the saturated model as your HO model. The saturated model means that each item gets its own mean, each item gets its own variance, and all possible covariances are estimated. So we have the magical keyword with here. With implies covariance. Whether or not it's a covariance or an error covariance is due to the context of the variables in the model. In this model, because the indicators are not part of a latent factor, they're just outcomes that are sitting out there with nothing predicting them. These are just the covariances between the indicators, and listing all of them on each side of the with means that you are requesting all possible pairwise combinations of covariances. So all 15 are being requested with this one line. And again, the stars are just to remind you that these parameters are estimated. They're allowed to be whatever they want, as opposed to parameters that are fixed, held equal to some constant with an @ sign as an alternative. So for instance, what would be shown right here. So the saturated model, if we were to fit that, then the height of the data under our model is the same height as the data under the saturated model. And because we spent all possible degrees of freedom, our chi-square value would be 0. So our model fits perfectly because it is just identified. So back to the regular one-factor model fit statistics. How did we do? Well, RMSEA is how much worse our HO model is relative to the H1 saturated model. So we want this to be as low as possible. Less than 0.06 or so is the traditional cutoff, and 0.17 would not be good enough by anyone's definition. We get a 90% confidence interval around that RMSEA point estimate. The wider the interval, That means you have the smaller the sample, and this sample is relatively large, about 1,100 people, so our interval is not too bad, not too big, I should say more specifically. And we also get this significance test result. This is a p-value that tests close fit. It's whether or not the RMSEA is less than or equal to 0.05, and decidedly it is not. So no good fit indicated by the RMSEA. Likewise, other fit indices. These are relative to the null model, so a different reference point. So whereas the chi-square model fit and RMSEA are asking how much worse is your HO model than the best possible saturated H1 model, these CFI and TLI statistics are comparing your model to the worst model. So they're asking how much better is your HO model relative to the independent's worst null model that doesn't have any covariances across the items. So you want these to be as high as possible. Greater than 0.95 is the conventional cutoff, and values of 0.7 and 0.5 are definitely not good enough. SRMR is another one that we want to be as small as possible. It's relative to the saturated model. This is on average how far off each of the correlations is between the model predicted correlation matrix and the one observed in the saturated model. And this is actually not too bad. We want this to be less than 0.08, so SRMR is less unhappy with the model than the other indices. And last but not least, this chi-square test has nothing to do with your model. You can ignore it. It is comparing the saturated model and the null model. So you can think of this as a test of whether or not there are any covariances across your indicators worth modeling. It will be the same result regardless of what you do. So you don't need to pay attention to this one as part of your fit diagnostic process. So the chi-square value of the fit of the baseline model, here's the math that shows you where that thing came from. The 15 degrees of freedom refer to the number of covariances up for grabs. And by the way, if you wanted to fit that baseline model for demonstration purposes, I did so here. Each item still gets its own mean in brackets. Each item still gets its own variance in just listing the variables by themselves. And now the with statement that controls the covariances, all of the covariances are held equal to 0. So this is fitting the null model. Of note, in terms of the fit statistics, this gives us an approximation for what the worst possible RMSEA would be for our data. So the worst possible RMSEA, if our model predicted no covariance whatsoever, is 0.26. The one for our current model, single factor model under investigation, is 0.17. So it's not that bad, but it definitely has a lot of room to improve. And likewise, CFI and TLI under the null model are 0 because that is what they're comparing your model to. So the null is the null, which means there's no difference at this point. All right, so how do we fix it? What we know so far is that our one-factor model is not good enough. So how do we fix it? We need to examine local fit, the idea of how far off is each of the covariances between what the model says and what the data say, and those are going to tell us where the problem is with respect to fit. So we talked about this, I think, on Tuesday, but just to review, we're going to look at what are known as model residuals. The word residual in this context means discrepancy. So we're looking at how far off each of the predicted covariances is between what the model says it should be and what the data say that it actually is. And you can ask for a normalized version of these statistics that are distributed sort of like z-scores. It's the discrepancy between the covariances divided by the standard error of the observed covariance, I believe. Standard error for sure. And so positive values indicate that the items are actually more related in the data than what the model says. Negative discrepancies indicate the items are less related than what the model says. And the other thing that you will get as diagnostic of local problems is what's known as modification indices, or what I refer to as voodoo. These are mathematically driven suggestions for how you can make your model fit better. And the key thing about these is that They will never suggest a new model. They will only suggest ways to repair the current model. So if we look at what those modification indices are for our current example, it lists a whole bunch of with statements. And what it means by that are error covariances. Because we only have a single factor model, that's the only thing it can come up with to improve the fit. So for instance, if we look at items 1 and 3, I've highlighted here, the first value, the 143, is the expected decrease in the chi-square test statistic of model fit if we were to introduce a residual correlation between these items. And the last column gives you what that residual correlation would be. Similarly, items 2 and 4 would result in an even better change in model fit, closer to the saturated model if we incorporated this suggestion, and the residual correlation would be 0.5. So rather than going through this atheoretical, mathematically driven list of suggestions, it can be more useful to look at what is the pattern that these suggestions are capitalizing on. What are they trying to fix? So more directly, what they are trying to fix is the discrepancy between what the model says the correlation should be between each indicator and what the data say. And so what we have here is residuals for correlations. M plus output, by the way, this is going to be towards the end of a very long file of output. I would recommend doing a find for these words so that you can avoid scrolling for so long to find these different tables. But residuals for correlation is in a correlation metric, what is the discrepancy between the observed and model predicted correlation? So for instance, between items 1 and 2, there's a negative discrepancy, so they are less related than what the model says, whereas items 2 and 4 are more related. Likewise, items 2 and 6 are more related. And these are the problems that the voodoo indices are trying to solve. So to put these correlations into a standardized format, we have the normalized version, and these are, yeah, I was right on the standard error of the observed. This is sort of like a z-score for how far off each of our correlations is. And these values really only have meaning, relatively speaking. They'll get very big in large samples, and so everything will look like it's a problem. But relative to within the table, you want to look at values that stand out. So for instance, I've highlighted a couple here. Situation 4 and 2, 2 and 6, and 4 and 6. These positive normalized residuals are all telling us that these items in reality have more of a correlation than what the model thinks they should. So they want to be more together. So I could add 3 error correlations to try and solve this problem, or I could reconsider the dimensionality of my model. The latter is going to be more useful in a way of capturing this additional relationship as a trait that I can relate to other constructs in an eventually bigger model. So rather than adding error covariances to sort of plug these holes, I'm going to elect to divide up my items into 2 factors, a factor that is consistent with the negative wording and a factor that is consistent with the positive wording. And as I noted in class, the reason that these indices are so much larger for the positively worded items is because they didn't load on the factor as much. The factor right now is doing a much better job of capturing the patterns of covariance among the negative items because those are more aligned with the factor. They had stronger factor loadings. The positive items are sort of left by the wayside. So they're the ones that are showing the problems. So here's my solution to the local fit telling me that items 2, 4, and 6 wanted to be more related than what the one factor model said they should be. Let's give them their own factor. So now on page 10 of example 4, I have a sit P for positively worded situation items that is measured by items 2, 4, and 6, and sit N that is measured by items 1, 3, and 5. And because I am estimating all of the factor loadings on each factor, I have to fix each of the factors' variances to 1 for identification. Likewise, because I am estimating all 6 intercepts for the items, I am fixing both factor means to 0 for identification. And the novel thing about this model with 2 factors relative to the model with 1 factor is right here. I am allowing a covariance between the 2 factors that can be different than 1. So the scale of these factors is such that the variance is 1. That means that this covariance indicated with width is actually in a correlation metric. So another way of thinking about what a one-factor model is saying about the data would be to make it explicit. So if I did this right here, I fixed the covariance to be 1. That is a one-factor model. 2 factors that are perfectly related is a one-factor model. So in allowing this covariance to be estimated, what we're testing is whether or not the covariance is less than 1. Is it not perfect? If it's not perfect, then 2 factors should fit the data better. So this estimated covariance being allowed to be something other than 1 is the new parameter that brings us up to 19. And if we look at the differences between the heights, it looks like we're much closer than what we were before with the one-factor model. More specifically, we want to compare our previous one-factor model to the current two-factor model. And I've written out the steps for that computation right here. This is not something that M+ will do for you. I have an entry in my spreadsheet that does the calculations. So I have the one-factor model log likelihood from before, the two-factor model log likelihood presently, their scale factors, their free parameters that are estimated, and I end up with this test statistic, a chi-square value of 342-ish on 1 degree of freedom. That means that the two-factor model fits significantly better, that adding that covariance between the 2 factors helped the data likelihood get taller. And this model also appears to fit relatively good in and of itself. So here's my chi-square test of model fit relative to a perfect model. It's still significantly worse, but by a much smaller margin than before. So our previous chi-square for how much worse the one-factor model was than the saturated model was 308. It's come down to 24. So that is a much closer fitting model to the saturated model, even though it's technically still worse. We have a lot of power in the current sample to make that distinction. The other fit indices also agree that this is a decent model. Our MSEA is down under 0.05 where we would like it to be. Test of close fit is not rejected, so it is within the boundary of 0.05. CFI and TLI are above the threshold conventional of 0.95, and SRMR is happy, value close to 0. And given our results, we want to make sure that these values aren't overly optimistic because of poor reliability. So we want to look at the standardized solution to get a sense of the strength of the loadings of our indicators. We'll talk about how we calculate reliability in the next class, but it's based on this information. And it looks like these are decently sized. So we're not in the situation where we get good fit no matter what because we have poor reliability. So that looks like each of these items has a sizable amount of relationship with each of their latent traits. So all of these are above 0.5 in the neighborhood of 0.6, which seems to be a reasonable minimum. In terms of the need to have 2 factors, the covariance between the factors, which is a correlation in this case because the factor variances are both 1, is only 0.56. So how forgiving you tend to be of things that happen to you that are no one's fault is not related lockstep with how not unforgiving you tend to be. So the idea that holding grudges is the opposite of being forgiving is not borne out by this analysis. These 2 factors, positively worded items and negatively worded items that are supposed to be measuring the same thing, do appear to be measuring slightly different things. They're still related, but the correlation is only 0.56. So the fact that our 2-factor model fits so much better than our 1-factor model is due to the fact that we're letting the covariance be this number, 0.56, instead of a covariance of 1. In terms of local fit, we'll look at that next. So skipping over the reliability part here for just a second. We have our residuals of correlation, so how far off are the model predicted correlations from the data generated ones from the saturated model, and the most off that any of these correlations is 0.1-ish, which I can live with. There's two areas of local strain or local misfit that are flagged. 1 and 2 want to be less related to each other, but they're already on separate factors, so there's nothing I can really do about that. And 5 and 6 want to be more related to each other's. So potentially I could add, say, an error covariance that would allow that problem to be remedied, but I don't have any theoretical reasons why I would want to do so. And global fit is decent enough to where I'm not going to take advantage of anything to try and plug this hole. The Voodoo has two different kinds of suggestions that it's making to improve the model fit. By statements, these are what's known as cross-loadings. So even though item 2 is already on the positive factor, model fit would improve by a chi-square difference of about 10 if it had a factor loading on the negative factor as well, and that factor loading would actually be negative. So I don't know what that would mean. I've got no reason to do it. I'm going to ignore these suggestions. These are error covariances that it wants, again, trying to plug whatever holes remain in this local fit matrix. And because I can't defend any of these, they don't make any sense given the content, I'm not going to incorporate those suggestions. I'm going to call it done. So where we left off then is the idea of how you would go about making your model fit better. And the most important thing I can tell you is that it has to make sense. You can't just go through these suggestions provided by the modification indices and apply them willy-nilly. You're going to get hammered in the review process because anytime that you're adding, say, an error covariance, that is an acknowledgement of unaccounted for multidimensionality that's part of your model. So it's what are you measuring? It's the latent trait and whatever this is, which is very theoretically unsatisfying. So the process of testing fixes to the model. We can do nested model comparisons in most cases to see what the impact of adding things is, or the impact of taking things away if we're trying to simplify the model. So I have a description here of the likelihood ratio test that is programmed into the calculator. I pointed out too in class that the way that you talk about the results of the model comparison are going to be guided by the purpose of the model comparison. So if you're starting with a model that has fewer parameters and you want to know if adding parameters helps, so if you go from a one-factor model to a two-factor model where you've added a factor covariance, or if you go from a one-factor model to a one-factor model that has error covariances, you're adding things with the goal of making the model fit better. So the significance test that you do in comparing the log likelihoods would have a result of better or not better. If the significance test comparing the models is significant, you reject the null hypothesis, what you means is that the fit has improved. You've made the model fit better. If the significance test, if the result is not significant, then you would say the model is not better with the additions that you've made, so they don't help enough to count. If you're starting from a more complicated model and you want to know if you can simplify, so for instance, if you start with a two-factor model, but the factors are correlated 0.95, a reasonable question would be, well, can I just collapse them into one? And is that going to cause harm to the model if I take away parameters? From that perspective, you would describe the results of your test as worse or not worse. A significant model comparison, if you take parameters away, means that you have made the model fit worse, and it wasn't a good idea to take those parameters away. If you have a non-significant result, that means your fit is not worse. And so a ready example of this is comparing our HO chosen model to the saturated model. We want our model to fit, not worse. We want the chi-square test of their difference to be not significant, meaning that we've gotten the data to be just as tall as the perfect model height, but we did so using fewer parameters. That's the end goal. So we'll see more examples of this when we look at testing invariance. And just a note here, technically speaking, you can use an alpha of 0.1 instead of 0.05 for testing parameters that are on the boundary, like a correlation that is of 1 because it can't go above 1. I've tried to care about this before and I just don't have the room to, so whatever. If you use the typical two-tailed alpha 0.05, it's going to be a slightly conservative test. You only really need to worry about it for borderline cases. So that is about where we left off. We'll talk about model comparability and what happens when you fix the model in various ways. We started talking about this at the end of class, but I want to go back over that in person on Tuesday. So we will wrap up for now. So thanks for staying with me. I hope my stream is still working, and I hope you all have a good weekend. Take care.